Okay, it says a 30 kilogram cart is released from rest. Oh, this is a good one. So we got to start 30 kilogram cart, right? That's a mass equals 30 kilograms. Now it says it's released from rest. What does that mean when we say from rest? Well, yeah, it means that we release it from rest, but that's a little clue. It means that the initial velocity is equal to 0 meters per second. Down a frictionless ramp, that means we're going to ignore friction. Another way to look at friction is 100% energy conserved. Now, one of my students, I think it was one of the AP students, said we do it that way because it's convenient, which is 100% true. Drops 10 meters, well, that's some sort of height, from the top to the bottom. So that means my initial height is 10 meters. And what is the bottom? What do you assume that means? That's your final height, and we can arbitrarily say that it's 0. We can pick our zeros for whatever we want. We like to pick the bottom as 0 because it makes it easier for us to do this problem. So it says, what is the change in the system that allows you to apply the constant change the system that allows you to apply the conservation of energy? Well, this is more theoretical than anything else. We're not going to, we might jump into the math in a second, but does everybody have that written down that I have written down? I'm going kind of fast. I forget that you guys have to write the words down. I see some. I can't tell if you guys are scribbling in your notebooks, drawing like anime or something, or if you guys are actually writing everything down. So I'll just wait a second. I still see a couple of people writing stuff down. So what do you think it is? Well, there's a change that occurs for sure, right? It starts at rest, and then it falls. So then it starts to move, right? So you could say that it goes from potential to kinetic, right? That's one possible solution. You could say that it goes from potential to kinetic, right? Potential means it's 10 meters high. Or you could just say that there's a transfer from EP to EK. But the textbook actually says that the cart moves. Same thing. Down. Now they do get pretty specific. They say down 10 meters. Okay. Okay. Does everybody have that written down? I'll wait a second. I see some people writing down. I wrote it down. You mean it takes you longer because you have to look at what I write down, then you have to write it down, then look back at the board and write it down, and you go back and forth, back and forth, back and forth, back and forth. The funny thing about notes is it's not the most exciting thing in the world, but it is the best way to learn. If you read your notes. All right, can I move on to the next thingy? All right. So it says the cart moves down 10 meters. Now, what are the states of the cart before and after the change? Well, it's basically what I listed before. We say at the top of the cart, it has an initial height of 10 meters and 0 velocity. At the bottom, it has 0 height and a non-zero velocity, which is a very specific way to say that. So it could have a negative velocity, right? Remember, it is falling down, but it's not 0. It's in motion. So I'll leave that up there for you guys to write that down. And then lastly, it says write down a statement of conservation of energy for the cart. Well, we're just going to say that the initial energy, the initial mechanical energy should be equal to the final mechanical energy. So go ahead and write that down. I'll leave that up for a second. So this is the thought process. We're going to solve this and figure out some stuff. Okay? So when I read the problem, notice that Mr. Adams immediately starts looking for clues, dissecting, jotting some notes down. This could mean this could mean that. Obviously, I have a lot more practice at doing these types of problems than you guys do. But that's what you should mimic when you go to do your homework. You go, well, what does this thing mean? Everything's a clue. What does this thing mean? From rest means it has an initial velocity, or if it says brought to rest means that it's the final velocity and it's 0. Rest always means 0 velocity, whether it's the beginning or the end, the initial or the final. Frictionless just means that we can make things convenient for ourselves and we'll ignore friction. If you were to really do this problem, you could factor in air friction, and it does slow things down. Okay. And it drops 10 meters. That's your height. And the bottom, you know, when you do these problems, it's nice to have a 0 in there because stuff cancels. Can you get that one? Okay. Okay, just set it down. I'm recording. Yeah, I know I was there, but you didn't ask me. Well, we'll talk about it later. We'll talk about it later. Recording. Sit down. Get your notebooks out. I would have given you permission. We'll talk about communicating better. All right, here we go. So let's do this problem. Okay. So let's figure out what do we want to figure out? Well, we can figure out the final velocity, right? So if I go in here and I say remember that your initial equals your final. I'm referring to mechanical energy. So remember, mechanical energy is 1/2 times the mass. The mass never changes, but we have an initial velocity squared plus the mass of the object times the acceleration due to gravity times the initial height. Lost my G there. Is equal to 1/2 times the mass times the final velocity squared plus the mass times the acceleration due to gravity times the final height. Okay? Now, what's interesting is if I take this whole thing and divide it by the mass, the very next line is, and I'm going to start writing it over here because we'll run out of room if I don't. The initial velocity, in other words, this cancels with this, which cancels with this, which cancels with this, which cancels with this. All those m's divided by m equal 1, so it all cancels. So I get 1/2 times the initial velocity plus the acceleration due to gravity times the initial height is equal to 1/2 times the final velocity squared plus 1/2 times the acceleration due to gravity times the final height. Well, we said the final height is equal to 0. So when I plug in the 0 here, this thing goes to 0, doesn't it? That's why I wanted to make it 0. Because I can cancel it out. It makes it a lot easier for me to do my math. Also, when we say from rest, bless you, this one is the initial velocity is equal to 0. So 0 squared times 0, right, times 1/2, the whole thing will equal 0. So those two go away. So my final answer then, or my final formula is G times H initial is equal to 1/2 times the final velocity squared. I'm going to take this and multiply it by 2. And then I'm also going to take this and multiply it by 2. The 2 cancels out with the 1/2. 1/2 of 2 is just 1. So then my final formula is 2, well, it's not quite my formula, final. 2g times h initial equals my final velocity squared. What do you think I do before I start plugging in numbers? I'm going to have to take the square root of this and also this. So then I've got the square root of 2 times 9.8 times the initial height, which is 10, is equal to my final velocity. So this is the velocity right before it hits the ground. Okay? So let's do that on the calculator, shall we? Don't worry, I'll pull it back up if you guys need to write it down. Just give me a second here. Let's get that out of the way. So I have 1/2 times 2 times 9.8 times, oops, times 10, right? Very frustrating. Let's try this again. It's not 1/2, it's 2 times 9.8 times 10, 14. Hey, that's pretty good. I'm impressed. So 14 it is. So my final velocity, and I didn't say it, but you notice that we're given meters and kilograms and stuff like that. So this final answer, whoops, would be 14 meters per second. So the final velocity of this cart, right, and when we say cart, we're referring to a roller coaster, right? It starts at the top of the hill that's 10 meters high, rolls down to the bottom, which we arbitrarily choose. So maybe we should have drawn a picture. Let me, we'll draw the picture so you guys can see this. So it starts way up here, comes down here. And here's my cart. Okay. This height right here, the initial height is equal to 10 meters. I'm going to arbitrarily, even though this might be higher than the ground, right? They're saying the bottom of the track, but it might be higher than the ground. So this height right here is the final height, which is 0 meters. Okay. And so as my car comes down here, by the way, before it's released, the initial velocity is 0 meters per second. And then what we were trying to figure out was, what is the final velocity when it gets down to the bottom of that hill? Well, we did the math, and it was 14 meters per second. Does the picture help you guys? My students used to make fun of me because I say pitcher. And they said pitcher is what you put water in. It's what you make lemonade in. And they said, are you referring to a picture? I said, yeah, pitcher. And then they would say, do you play baseball? I was like, I did play baseball. Oh, were you the pitcher? All right. Any questions on this one? Did everybody have all that stuff written down? I'm sorry. Does anybody need anything else off of this? Okay. Yes. Oh, sure, yeah. Now we're going to come back to question D in a second, but I wanted to do the math, and I wanted you to have it written down because I want you to see it. I want you to see how you actually do the problem. So, but what you do, just to kind of come back, we have to figure out what the change in the system is. We have to state what the car was before and after the change. And then we write down the conservation of energy, right? The total mechanical energy in the beginning has to be the total mechanical energy at the end. And that allows us to actually solve for things like final velocity. And you could do the same thing. If we weren't sure how high a roller coaster was, and we had like a radar gun, and we could figure out how fast the roller coaster was at the bottom of the hill, we could do the same thing and figure out the initial height. Right? Because we would assume at the top of the hill it's 0. Okay. Now we'd have to figure out what the friction could be, possibly, both air and the actual friction of the wheels and stuff. And we'd have to calculate the rotational energy. So this problem is a convenient problem to practice conservation of energy. There are other things that we would have to factor to do that. But we could get a good approximation as to how high that first drop is. Okay. So then, yeah, let's finish this up. So what form of energy is 0? Well, the initial kinetic energy was 0, and the final potential energy was 0. We rigged it up that way. So write that down. And then we went through and we did all the math, and we got 14 meters per second. So write down the question and the answer. Now this square root of 2gh works when you try to find final velocity. You could use that formula. I never give kids that formula because I'd rather you do the total conservation of energy. This formula, the square root of 2gh, only works if you have 2 zeros, and it has to be the initial kinetic energy. Something starts at rest, and then you're going to the bottom, all the way to the bottom, where your final height is 0. That's the only time this works. This equation up here always works. Always works. This only works in a certain situation. But this always works. And it seems like a lot of work, but if we're honest, you guys are going to not all of you, but some of you will forget that this only works when you have a zero initial kinetic energy and a zero final potential energy. And so you don't even have to worry about that if you just use this equation. Do a little extra algebra. It's just a couple extra steps to get you to this if you need to do it. Okay? Any other questions on that one? I think we have one more example, and then I'm going to give you a homework assignment. I see that you guys are writing this down, so I'll just wait a second. All right, let's see what's next. So I want you to think about this. Which of these statements is not true for a closed system? Well, this is true for a closed system. This is true for a closed system, I think, unless there's a trick in there. I think D is the false one, right? Is the potential energy always conserved? Let's see. Yeah. So write down the question and then write down the answer. Does everybody have that written down? Yes. Okay. Hey, that's it.